Today, we will be implementing the procedural modeling of the central monument of the 1956 Hungarian Revolution and War of Independence using Blender's geometry nodes. We start with the mesh circle node, and to get a triangle, we set vertices to 3. And set the fill type parameter to n-gons. Next, we isolate the specific vertex where the index number is equal to 0. We then connect the separated vertex data to the geometry proximity node to derive a field of distance values. From the distance socket, we plug the output into a map range node to normalize the values from 0 to 1. We then adjust the output range of the map range node by setting the to-min value to $1 and the to-max value to 0. This inversion ensures that the separated vertex proximity corresponds to the highest normalized value of 1. Next, we distribute points across the faces of the geometry. We then utilize the previously normalized proximity value to drive the density parameter of the distribute points on faces node. Next, we establish a specialized operation to execute a loop over each element in the point domain. Within the current iteration for each point, we generate an independent curve line primitive. Next, we connect the distance field output from the previous geometry proximity node to the initial input of the for each element node, allowing the distance values to control the factor parameter of the trim curve node within the loop, thus dynamically adjusting the length of each generated curve. We then plug that distance value into a secondary map range node to remap the field values and control the resulting length parameter of the columns. Now we proceed to the phase of giving the current curve lines a column-like appearance using the curve to mesh node, utilizing the curve quadrilateral as the profile curve. Now we focus on the column density within the triangle. This density, generated by the proximity node from the previously separated vertex, appears somewhat linear. I aim for a more radial appearance, and to achieve this, I will subdivide the base triangle mesh to level 6. Next, from the original triangle geometry, we utilize the extrude mesh node. Subsequently, we need to observe, or access, the index number for each respective vertex. Next, we set the position for the vertex with an index number equal to 4. Essentially, we are snapping this vertex to the original position of the vertex that had an index of 1 on the primitive triangle. We perform the same operation for the vertex with an index number equal to 5, snapping its position to the original location of the vertex with an index of 2 from the primitive triangle. We then use the offset input to control the z-axis value of those vertices. This effectively resets the vertice's z position and reapplies control using the designated z-offset value. Now, we synchronize the to-min and to-max values from the secondary map range node and feed them into both the offset value of the extrude mesh node and the z-axis value of the set position node. And with that, we have completed the main volume, which is now ready to be cut using a mesh Boolean operation to form the monument's sharp, metallic apex. From the original triangle mesh, we now connect it to a bounding box node. We determine the total dimensions by subtracting the min vector from the max vector. This resulting dimension vector is then multiplied by a factor of $2 and fed into the size parameter of a cube primitive. This guarantees the creation of a robust cubic geometry that is sufficiently larger than our main block. Upon encountering the manifold error due to preparation oversight, we rectify the source mesh by utilizing the flip faces node on the original triangle. We then combine this with the extruded mesh and apply merge by distance to unify any duplicate vertices, ensuring a closed, manifold volume. Finally, the as-edge boundary node serves as a safeguard to verify the clean topology before the Boolean operation. Next, we separate the columns based on their position. Since we previously converted the mesh into instances using the for each element loop, we must select the instance domain for the separate geometry node. Following this, we set up the materials for both the columns and the apex section, cut by the previous mesh Boolean node. The materials are kept simple for clear distinction between the wood and iron elements. The final step is to organize our node groups by framing and appropriately naming them. This ensures clarity and prevents confusion or getting lost the next time we open the file. Thanks for watching, and I'll see you in the next tutorial.